In part 2 of the lecture video, we're going to talk about human vision, and in terms of homework 7, this should help you do problems 10 onward. Okay, so components of the eye refract entering light, and they basically function as an overall lens to then focus images onto the back of the eye, which is called the retina. Now, the components in the front, there's a few of them. First, we have the transparent front part of the eye, which is called the cornea, and the index of refraction there is 1.38. And then there's the aqueous humor fluid here that has an index of refraction of 1.34. And then we have the lens itself that has an index of refraction of 1.41. And out here, of course, we have air. So when we have light rays coming in, there's some diffraction happening through each component. But when we're analyzing the eye, we're going to use a simplified model of these components. And this simplified model basically includes treating the cornea, aqueous humor, and lens as one lens that is going to refract light and then focus images onto the retina. Now, the typical distance from the lens to the retina for the average eye is about 2 centimeters. Oops. So what we have going on is we have an object somewhere out here, and the distance from the object to the front of our eye, that can vary depending on what we're looking at. If we're looking at, let's say, a computer screen, that might be 50 to 100 centimeters. So this is the object distance. On the other hand, if we are looking at something far away, you're at a sporting event or just staring out into space, sitting at the beach, that object distance can go from hundreds of meters out to infinity. Now, the question you might ask is, how is it possible for our same lens? So, okay, let's first remind us of the lenses equation. We have 1 over dO, the object distance, plus 1 over di, the image distance, is equal to 1 over the focal length. The thing that's staying fixed in our eye is di, basically image distance, the distance from the lens to where the image needs to form if it is to be sharp and clear and not blurry. And that remains to be 2 centimeters. So if di is fixed, this never changes. And we're looking at a whole range of object distances from 20, 30 centimeters all the way out to infinity. How is it possible for us to just use one single lens in our eye to look at all of this? This is where accommodation comes in. So what's accommodation? There's muscles in the eye that adjust the shape of the lens to change the focal length, to change f, so that objects at different distances form images on the retina. So we have relaxed vision, and then we have accommodated vision. Relaxed vision is when you're focusing on distant objects, something far, far away. And then accommodated vision is when you're focusing on nearby objects. And you've probably experienced the difference between these, mostly because of accommodated vision. So if you've been doing homework all day or playing video games all day and sitting in front of a computer screen, you've noticed that your eyes after some time will feel tired. And this is because you've been using your accommodated vision for a long period of time. On the other hand, if you're sitting out on the beach and staring out into space, you can sit there and do that for hours. Your eyes, you might get sunburned, but your eyes don't necessarily feel tired because that's when your eyes are relaxed. They're not focusing on any nearby objects. The range of distances that we can see is approximately 25 centimeters to infinity. And I encourage you to pause the video and test this 25 centimeters. Basically, take a Post-it note, take a book, take something that you have some words written on, hold it out at arm's length away, and slowly bring it closer and closer, and figure out when do the words become blurry? When can you no longer crisply read what words are written on that piece of paper or that Post-it? And if you have a ruler around, you can measure that distance, and it'll be pretty close to 25 centimeters. Now, more terminology. We have, for our vision, we have the near point, and we have the far point. Near point, which for most people, this is 25 centimeters. This is the closest distance we can see clearly. And this increases with age. So as you get older and older, you won't be able to focus on objects that are maybe 25 centimeters. Maybe the object needs to be out at 26, 27, 30 centimeters. And eventually, you might even need eyeglasses to be able to see nearby objects. And then the far point is the farthest distance we can see clearly. And for someone with perfect 20/20 vision, that is out at infinity. And for people who don't have perfect vision, you can figure out what this far point is, and we'll do some calculations of that. These two slides I'm going to skip, but I encourage you to look at this slide and think about this next clicker question. This is just conceptually getting you to think about shape of lenses and the focal length. Okay, now let's talk a little bit more about accommodation. So we talked about relaxed vision versus accommodated vision. So relaxed vision, you have rays coming out from infinity and they need a little bit of bending to focus on the retina. In the relaxed eye state, our lens is thin. And you can think through this previous question and convince yourself why in this state a thin lens is what corresponds to relaxed vision. And then in the other case, when you're looking at close by objects, we're using the accommodated vision. This is where the muscles engage to increase the thickness of your lens, and you have a thicker shaped lens. And here, basically more bending, more refraction needs to happen by your eye to clearly focus the image onto the retina. Okay, let's do some actual calculations to make sense of this. So we want to figure out the range of the power of the eye. And just to remind you, the connection between optical power and focal length is power is measured in diopters, and it's 1 divided by the focal length. And the units of diopters, D, is the same as 1 over meters. That means if you're plugging in focal length to find power, your focal length should be in units of meters. Okay, so let's work on this problem. What is the range of focusing power of an eye that can clearly see objects from 25 centimeters to infinitely far away? Assume that the retina is located 2 centimeters behind the lens. As I mentioned earlier, basically our image distance for our eyes is fixed. We need to take some kind of object and we need to focus it on the retina, which is 2 centimeters away. So let's go ahead and start first with the distant vision. Distant vision means, so here's the diagram. You have the lens of your eye, you have the retina 2 centimeters away, you have an object far away. Basically let the object go to infinity. What focal length of the lens do we need to focus the image on the retina? Well, let's use lens's equation. 1 over f equals 1 over do plus 1 over di. For object distance, we're going to basically take the limit as object distance goes to infinity. So when you do 1 divided by a really large number, we get basically 0. So this fraction goes to 0. Then we have 1 over di, 1 over 2 centimeters. So pretty much 1 over f equals 1 over 2 centimeters. That means the focal length of the relaxed eye is 2 centimeters. And in a minute, we're going to calculate what power this corresponds to. Next, let's find the focal length of near vision. So when you're looking at nearby objects, and the closest object that we can focus on our retina is 25 centimeters. So we put our object at 25 centimeters away. We want to find the focal length of our eye when the image distance is 2 centimeters. So we plug everything into this formula, and we get that the focal length needs to be 1.85 centimeters. So the focal length is basically ranging from 2 centimeters to 1.85 centimeters for relaxed and accommodated vision. Now let's calculate the corresponding power. Basically do 1 divided by 2 centimeters, but we need to convert to meters because that's what diopters are basically inverse meters, not inverse centimeters. So convert each of these to inverse meters, and we get 1 over 0.02 meters, meaning 50 diopters. And then for the accommodated vision, we get this. So this is the minimum power of our eye. So P min is 50 diopters, and P max, the max power of the eye, is 54 diopters. All right. I encourage you to pause the video and make sure that you can digest this information and do this example on your own. The next thing we'll talk about is vision defects. So maybe some of you are nearsighted or farsighted, maybe you have 20/20 vision. What does it mean to be nearsighted and what does it mean to be farsighted? Let's talk about that next. So vision defects happen when the image is focused off the retina. Nearsightedness, also known as myopia or having myopic eyes. The eyes focus the image in front of the retina. So what can possibly cause this to happen? There's a few different reasons. Either the lens is too strong, so the image is being focused somewhere in front of the retina, or another reason could this be the eye is too long. So in the process of focusing the image, DI is no longer the 2 centimeters, which is the typical length. And the consequences of nearsightedness are you have blurred vision for distant objects. So when you're looking at faraway things, they appear a little bit blurry. On the other hand, hyperopia, farsightedness, eyes focus the image behind the retina. So this looks something like this, and this is caused by either the lens being too weak, so not being able to bend the so the accommodation of your lens not being able to bend the rays strongly enough to have the image focus on the retina. It gets focused back here, so it appears blurry. And another reason for this could be the eye is too short. So as your accommodated lens is focusing the image, instead of focusing at that 2 centimeters away, it's focusing somewhere back here behind the retina. And the consequences of farsightedness are basically blurred vision for nearby objects. So how do we correct this? So first, let's start by talking about correcting myopia. So myopia, again, just to remind you, is when the lens is too strong or the eyeball is too long and the image is being focused in front of the retina. So here, we use a diverging lens. And what the diverging lens does is it takes incoming rays that are converging too much and basically forming the image here. What the diverging lens does is bends the rays outward. So these are rays that are coming from distant objects. And remember, rays from distant objects are parallel rays coming in. And the diverging lens bends these rays outwards so that the quote-unquote too much bending or the retina being too far back we can still match up our focused image to where the retina is. So diverging lens bends these rays outward, and then our accommodated eye can focus the image here. How do we figure out? So let's say we have somebody who has myopia and they can't see faraway objects. Well, the first thing the optometrist is going to figure out is what's the furthest object you can see. You can't see objects all the way out to infinity, but you're going to have your eye is going to be able to focus properly objects up to some distance. And depending on what that distance is, it'll determine what power lens you need to correct your myopia. Let's do a calculation. And before we do a calculation, let's just talk about what this diverging lens effectively is doing to the object and then the image then your eye looks at. So let's say we have a distant object at some distance far away. The corrective lens takes that distant object and makes an image of it at a close by point, and this is going to be your far point, meaning the furthest distance that you can actually see clearly and can focus an image on your retina from. So lens number 1 is the corrective lens, forms an image here. Now this image becomes the object that your eye lens is looking at, and then this object can then be focused on your retina. So let's do a calculation for, we have a nearsighted person whose far point is 40 centimeters. So basically the furthest objects that they can clearly focus is 40 centimeters. What should be their contact lens prescription to enable clear vision of distant objects? So what does this all mean? 40 centimeters is the furthest object that the eye can see a focused image of. We need a diverging lens to take the object all the way out at infinity, a distant object, and form the image at 40 centimeters because that's the far point, so that the eye lens can focus now this image at 40 centimeters onto the retina, because this is the furthest distance that our myopic eye can focus the image from. So when we're solving for the power of the corrective lens, we're going to start with the image distance. We want our corrective lens to form an image at our far point. So we want it to form an image 40 centimeters in front of the eye. Well, that image is going to be basically in front of the lens, and this is a virtual image, and you can see that by the rays being extrapolated. So that is a negative 0.4 meters is the image distance. Where does the object need to be placed? Well, keep in mind, we want to be able to see distant objects. Basically, object distance going out to infinity. So we want to be able to see objects that are infinitely far away. And then if we figure out the focal length of this corrective lens, then we can find what power that correction needs to be. So we start with lens's equation, 1 over di plus 1 over do is equal to 1 over f. Well, we know we're taking the limit as do goes to infinity. Well, if you do 1 divided by a really large number, you know this goes to 0. So we have 1 over di, so 1 over negative 0.4 meters is equal to 1 over f. That means that f is equal to negative 0.4 meters. And so far, numerically, things make sense because diverging lenses have negative focal length, and that's what we have. So to figure out the power, we just do the inverse of the focal length. So we're going to do 1 divided by negative 0.4. And that gives us a power of negative 2.5 diopters. And again, just to remind you, make sure that your focal length is in meters when you're calculating this. Also, to make things a little bit easier, you don't have to do this extra step. Remember that 1 over the focal length is just the power. So in your equation, you can just replace 1 over f. So we can write 1 over di plus 1 over do is equal to the power of the lens. So you can calculate the power this way too. I wanted to show you this step just to relate things back to focal length, because that's a physical quantity that we've been working with when we draw these ray diagrams. Okay, the next thing we're going to talk about is how to correct hyperopia. So hyperopia is farsightedness, meaning you can see far away objects just fine. But then when you're trying to focus close by objects without the lens there, we're looking at the blue rays, so no bending happening through air. And then when your eye bends the rays, it's forming an image that is behind your retina. So the focus is back here. What we want to do is basically be able to bend these rays even more so the image forms on the retina. Well, to bend the rays further, we're going to need a converging lens. So you use a converging lens to correct hyperopia, and it pretty much makes an image beyond the eye's near point. So let's talk about what this near point is. The near point for someone who's hyperopic is the closest distance at which your eye can focus nearby objects without any correction. Now, for people with perfect vision, that near point is 25 centimeters. So basically we want our eyes to be able to focus something that's as close as 25 centimeters or further away. Closer than 25 centimeters, basically that's like pretty much right up against your face with not a whole lot of distance. And we don't have the need to focus things that are any closer than that. When you're reading, you keep a book or your screen anywhere from like 30 to 40 centimeters from your face. So what the corrective lens does is it takes something that's basically at 25 centimeters and it's going to put that back at your near point. So when we're talking the image distance and the object distance for this lens, well, the object is going to be at 25 centimeters. And then the image is going to need to be formed at your near point, because once the image is at your near point and your eye lens is looking at it, your eye lens can then focus that perceived object without any further correction. So let's go ahead and summarize. We'll do an example of correcting hyperopia in class on Tuesday. So in summary, we've talked about a set of lenses. When light passes through two lenses, the image formed by the first lens becomes the object of the second lens, and the magnification overall by this set of lenses is just the product of the two magnifications. And in terms of eyes, a relaxed eye has a object distance that is at the far point, meaning your muscles are completely relaxed and focusing on faraway objects, and they're able to form the image at your retina, which typically is 2 centimeters. And then when your eye is as accommodated as possible, meaning your muscles are as engaged as possible, we're looking at the near point, and typically for a human with perfect vision, this is 25 centimeters, and then the image distance, again, to your retina is 2 centimeters. Myopia is nearsightedness, eyes are too strong, corrected with a diverging lens. Hyperopia, farsightedness, eye lens is too weak, corrected by converging lens. All right, this should get you through most of your assignment. I'll also be postponing the homework deadline from Monday afternoon to Tuesday night, so that you can also get some help from the examples done in class.